recording. Okay, so today we're going to be talking about functions. We're going to be talking about functions. Uh, yeah, so a function, what is a function, right? A function is a very general idea, and that you can start by saying that if a and b are sets, then a function from a to b is a rule which to every element x in a assigns a unique element y in b. And then we have this image for its representation. And we also say that the y being equals to f of x is the image, y is the image of x under the function f. And then we have the example about the husbands and their wives, which is no pun intended. Um, and then there is a couple of details, right? So now we're going to go through definitions that depends on all those details. So for example, a function from a to b must assign a value in b to every element of a without exception. Now, suppose that we have a mapping. Instead of having like one wife per husband, we have a polygamy system. Polygamy system, I think that's how you say it. In which a husband may have more than one wife, right? So if that's the case, then it's not a function, right? Because for the same value in the A set, you have two or more possible outcomes in the B set. So a function, if we're trying to establish a function from A to B, it must assign exactly one image of to each element of A. If f is a function from A to B, it is customary to use this description, those symbols to describe it. And then more nomenclature. So the set A is called the domain of f. The range of f is a subset of B, which consists of all the images of elements of A. Which brings to the picture the idea that you can have a set of B, but not all of the elements in B are being mapped. Not all of the elements of B are is part of the image of the thing. And then in the case of the function illustrated here, A, B, and C is the domain of F. So these are the things on the input set, let's say. And X, Y is the range. Uh, those live in the B set. And Z is not in the image. Incidentally, this function f can be represented in the simplified notation. So this is the matrix representation, where the first row are the inputs and the second row are the outputs. And this is useful for when A is a finite set. The elements of A are listed in the top row, and beneath each element of A, it's its image. And now, and now more details. So it may perfectly well happen if f is a function from A to B that two or more elements of A have the same image, such as this case. So the image of A and B in the set A is the same x in B. So for example, if we look at the function immediately above, we observe that A and B both have the same image x. If f is a function for which this kind of situation does not occur, then f is called injective. So in an injective function, you will not have the situation where two or more elements of A are mapped to the same element in B. But of course, we're going to describe the situation in a different way by saying that if f of x1 is equal to the f of x2, this implies that x1 is equal to x2, which is saying the same thing in different terms. I would say that I think this way of explaining things is less intuitive to me, although it's more precise, right?
Yeah, this actually is easier to manipulate formally
Yeah,
because you can use universal quantification to
yeah,
define things this way.
yeah. It's more precise. It's probably more useful for manipulation, but I don't know. I find it to be less intuitive. Especially because to me this is more like a consequence of the other way of describing it and not the other way around. But anyway, math people. So a function f is called injective if each element of B is the image of no more than one element of A. The intended meaning, of course, is that each element y in B is the image of no two distinct elements of A. So that's what we just said, and this is what I said before about describing this property in this way. If f is a function from A to B, there may be elements in B which are not images of elements of A. If this does not happen, that is, if every element of B is the image of some element of A, we say that f is surjective. So this is talking about the z here. So the z in B not being in the image, not being in the range of f, means that this function is not surjective. But if this does not happen, then it is surjective. A function f is called surjective if each element of B is the image of at least one element of A. And the at least here means that the definition of surjective and injective are orthogonal, which is, well, expected. But we're going to combine those two definitions soon anyway. This is the same as saying that B is the range of F. This image should not be here, but okay. Um, Now suppose that F is both, right, injective and surjective. By the definitions 1 and 2, each element of B is the image of at least one element of A and no more than one element of A. So this is the definition of surjective, and then this is adding the injectivity is restricting even more. So each element of B is the image of exactly one element of A. In this case, F is called a bijective function, or a one-to-one correspondence. And then that's what we're going to define as bijective. It is obvious that under a bijective function, each element of A has exactly one partner in B, each element of B has exactly one partner in A. And now we're going to talk about combining them. Marinho, you want to say something?
I just want to point out that a bijective function is one half of an isomorphism.
Yeah. Yeah, we're going to talk about the inverses in a bit. The most natural way of combining two functions is to form their composite, which is to compose them. So the idea is, suppose f is a function from A to B and g is a function from B to C. We apply f to an element x in A and get an element y in B. Then we apply g to y and get an element z in C. So this becomes a chain of operations, right? So you are here, you use f to go to here, and use g to walk through here, and that's how we do things. And then, yeah, we call this composition, and here's the definition. Let f be this function and g be this function. The composite function denoted by g after f is a function from A to C defined as follows. This is the notation, with quantification being explicit here. So for example, consider once again a set A of married men and a set B of their wives. Let C be the set of all the mothers of members of B. Let F be this function, be the rule which to each member of A assigns his wife, and G the rule which to each woman in B assigns her mother. Then G after F is mother-in-law function, which assigns to each member of A his wife's mother.
That's a very silly example.
I think those are awesome examples, actually. All the chosen examples, they are in the same universe. So you have like marriage, and then we have polygamy, then we have the mother-in-law, and it's all in the same universe, and we are using it to explain the ideas. I like it. For another more conventional example, let f and g be the following functions. So 2x and x plus 1. So multiply by 2 and add 1. Their composites are the functions g after f and f after g, which create two different functions. Because one of them says add 1, then multiply by 2, and the other one says multiply by 2 and then add 1. It is an important fact that the composite of two injective functions is injective, the composite of two surjective functions is surjective, and the composite of two bijective functions is bijective. In other words, if those two functions are these, then the following are true. So if you have two injective, they still are injective. If they are both surjective, then the composite is surjective. And I think this is pretty obvious if you just draw the diagrams. It's like if you draw the diagrams with those assumptions in mind, the conclusion is gonna follow in the drawing itself.
Uh, I would just like to state explicitly the opposite, which is that the composite of two non-surjective functions is not necessarily non-surjective. And that is kind of easy to find a counterexample, but I actually that was a mistake I made on one of the exercises, which is why I'm pointing this out explicitly.
You're saying that if the composite is non-surjective, that doesn't mean that both of their members are non-surjective.
I mean, if both of the members are non-surjective, the composite may still be surjective.
Ah, okay.
That's easy to see why, but if you don't
How
state
can
it explicitly, it's also easy to fall into the mistake of thinking that is the case, as I did.
Marinho?
how can it be non-surjective if G is surjective?
What do you mean exactly?
Like, say you are composing G after F, and G after F you know is not surjective. How can you get G being surjective out of that as a possibility?
Uh, that wasn't actually what uh, I was trying to say.
Mm,
Wait, so I think
or
it's
rather,
worthwhile repeating what you said. So you're saying that if the composite is non-surjective, what does that mean?
No. If F and G are both non-surjective, then the composite may or may not be surjective.
okay, let me rephrase my question. How can you get um, how can you get a surjective function out of a G that's non-surjective?
Yeah,
You
this question matters to your argument, too.
you can conditionally like define a condition such that you map the conflicting elements to different elements on the resulting set.
No, that's injectivity. I'm asking about surjectivity.
Actually, I had the counterexample. I forgot about it because I did not write it down. That is fun. Let me think about this again.
No, while you think about it, let's finish this so we can go to the exercises. Let's tackle each of these claims in turn. We will suppose that f and g are injective and prove that the g after f is injective. That is, we'll prove that um, if this is equal to that, then x must be equal to y. Suppose that they are not, they are different. Well, suppose this equality. That is this. Because g is injective, we know that f of x must mean f of y. And because f is injective, that must mean that x is equal to y. Next, let us suppose that f and g are surjective and prove that the composition is also surjective. What we need to show here is that every element of C is g after f of some element of A. Yes. Well, if a z is contained in C, because g is surjective, then gx is equal to g applied to y for some y because f is surjective. So y is equal to f of x for some x in the input set. Thus, we say these things. Finally, if f and g are bijective, they are both injective and surjective, by what we already proved, g after f is injective and surjective, hence bijective. Yeah, so this is essentially, how should I say it? These two proofs are about using the properties of what the names mean and going up from there, right? So if you have a z in C, and then you know that you can say that x is equal to g applied to y because f is also surjective. Then you can keep doing these equalities until you find a definition of the composite, and then there you have it. You have that this is equal to z, which means that this is surjective. Um, and now we're going to talk about the inverse. So a function f from a to b may have an inverse, but it doesn't have to. the inverse of f, if it exists, is a function f to the power of -1, or f inverse, from b to a, such that x is equal to inverse of f on y, if and only if y is equal to f equals to f, y is equal to f of x. And this is the other side of the isomorphism that Marinho was talking about. It's not defined formally, but this is the intuition about it. Roughly speaking, if f carries x to y, then inverse of f carries y to x. For instance, returning for the last time to the example of the husbands and the wives, it's very simple to see the inverse, right? Because if f is the rule to which to each husband assigns his wife, the inverse is the rule which assigns each wife assigns her husband. If you think of functions as rules, then the inverse of f is the rule which undoes what f does. For instance, if f, it's very interesting that the verb that was chosen is do.
By the way, never mind. My counterexample was silly.
Okay.
I wrote it down, and now it's obviously wrong.
Yeah, but it's very easy to put yourself in those holes, Tivo. So don't feel bad about it. Don't feel bad about it. It happens to all of us. Maybe not doesn't happen to Marinho though. Only for me and you.
No, it happens to me as well.
Oh, I mean, that's why you have book club, so you can state your wrong assumptions and realize you're wrong.
Yes, we are in the book club to be enlightened by Marinho Sensei. That's true. For instance, if f is a real valued function double, and the inverse is divided by 2, and that's how we can do the go back and forth. Oh, I was talking about the verb, right? I was talking about the verb. I don't know, I have a programming brain, so I would expect that math people would use the verb map instead of do. But this guy chose the verb do.
I think that's a very appropriate verb.
I don't know, doing kind of have the feeling of doing an effect. So, can you always undo that? Who knows? Which functions have inverses and which others do not? If f is a function from a to b is not injective, it cannot have an inverse. Why? Because if f is not injective, these non-dotted lines hold, which means that if you try to do the inverse, you're going to be obligated to do the dotted lines, which doesn't follow the definition of a function. So very nice pictorial representation, in my opinion. Clearly, x1 equals to f inverse of y, and x2 inverse of f on y. So the inverse of y is ambiguous. It has used for two different values, and this is not allowed for a function. If
Can I just
f,
say that
yes.
this diagram looks like a pair of scissor blades?
Sure. It does, so sure. If f, a function from a to b, is not surjective, then there is an element y in b which is not an image of any element of a. Thus, the function does not exist because the definition of function also says that we have to grab all of the elements of the input set, and because it's not surjective, there will be elements hanging. So inverse of f cannot be a function from b to a. So it's very nice that the injectivity and surjectivity properties already give us for free the existence of not of an inverse. That's kind of nice. Because that means that if you know f has an inverse, you can already know things about it. That's nice. It is therefore obvious that if inverse f exists, f must be injective and surjective, that is, bijective. On the other hand, if f is bijective function from a to b, its inverse clearly exists and is determined by the rule, and that if y is equal to f of x, then inverse of f on y is equal to x. So yeah, bijectivity gives you already the inverse existence information, which is nice. And here's the image representation of that. Cool. And furthermore, it is easy to see that the inverse of f is also a bijective function. So to sum it up, a function f has an inverse if and only if it is bijective. In that case, the inverse of f is a bijective function from b to a. And there we have it, folks. Functions. There we have it. So 20 minutes to talk about all about functions. Now we have 40 minutes to do exercises. So which exercises you guys want to talk about? So let's start with exercise A here.
All right.
So is there any one of these 7 exercises here that you think it's interesting to talk about, considering that we have to prove whether or not the function is injective or surjective?
Uh,
I just want to say that it was exercise 4 that was the source of my confusion, because my original approach was to try to define x in terms of y and see if that is injective and surjective. And that has a square, which is not surjective. So, like, my original thought was, okay, that's not clear. That's clearly not surjective. So it that maps to more than one value. So
Wait, you said that this is clearly not surjective.
if you try, okay, you have f of x in terms of x. Sorry, if you try algebraically rearranging the terms such that you get the inverse of that, then one of the members is x squared, which is not
right, because in
defined.
general, if you try to get the a square root or any even root for that matter, um, the value can be either positive or negative,
Yeah,
right?
but that's talking about injectivity. Devo is talking about surjectivity. That's why my question.
But it means the inverse is not injective.
No, yeah,
And in fact, there is a very trivial counterexample, which is -1 and 2, if I'm not mistaken. Like if
minus
you
one and
plug it
what?
in,
Let's try
it
that out. So let me go
minus
to
1 and
the.
2. If you plug it in, you get the same value.
Okay, so I have my thing here. So f of -1, you said, right? So this is -1 plus 3, which is equal to 2. And what is the other f?
3. 2,
3.
sorry. 2
Okay, so 2.
becomes 8, and 6 becomes 2 again.
2. So this means that it is 8 and 6, which is equal to 2, which means that this is not injective. Right.
And so, just to explain, the source of my confusion was that I drew all, I algebraically manipulated the terms to get the inverse, and then asked myself, does the existence of a square here imply that this is not surjective or injective? And somehow I convinced myself that that was not necessarily the case. But my counterexample was silly.
Mm-hmm. Okay, so to prove um to prove is the f of x in 4 surjective or not? We just proved that it is not injective, right? How would we go out to prove that the surjectivity of f? We can do the inverse thing that Devo was talking about, right?
Surjectivity. You can probably invoke some number theory to do that, but honestly, that's not too interesting to me, so I didn't bother doing that. Like, because here's the thing, this is a function on numbers, right?
Yeah, I think we would have to do what Devo said, man, to do this one. We would have to do y equals to the thing and isolate x in terms of y. I think we have to do that. Which is a pain in the fucking ass, right? Because you're gonna have to do y is equal to I don't know, x third 1 minus 3
I
divided by
eventually I did that. I eventually got cube root of x to the fourth power minus 3x to the squared plus 3. If you want to go down that route.
But if you found an inverse, that means that it is surjective, right? Wait, you cannot find an
No,
inverse of
no,
this
no,
because this is
no.
not
Well,
injective, right?
To prove that this is surjective, or to disprove it, you have to basically you have to prove that it is either defined for every input or not. Because like if you
it
graph this
is.
out,
Go. Finish Marin first.
No,
because like
yeah.
if you graph this out, you basically have to prove that this function does not diverge at any point, essentially.
I agree with what you said, Tiv.
I might be confusing both definitions, but it is not injective because two values map to the same value, but it is
Yes.
surjective because it has an output for every value of the reals.
No, but the question of
If
surjectivity is the other way around. You have to ask if all the values of reals are in the image of f.
they are.
No, then it is surjective. What Marinho said, which is the graphical representation of the same statement, is that this does not diverge, right? So that's what Marinho said.
Yeah, you have to prove that to say, okay, this is surjective because you can get every possible number out of this for whatever.
Yeah.
Like there's some number that you can give it as an input that gives you that output. There may be more inputs that map to the same output, but that doesn't matter for surjectivity.
Yeah. Um, yeah, but I'm a little bit uneased by how I would do that. Like stating what we have to do is one thing, but doing it is another. Tevo said that he managed to find an inverse of this function. I think that's gonna. I don't understand how that's possible, given that because this is not injective, this cannot have an inverse.
No, actually it can.
Really?
Oh
It's
no,
sitting
actually
here.
no. Actually no. Never mind. I got confused.
Tevo, do you
Yeah,
see what I'm saying?
Uh,
Read this first line here of in italics here.
yeah. No, I was thinking of something
I
else. You
did
were right.
manage to manipulate the function algebraically such that you can get an inverse function, but I haven't
Uh,
checked if this inverse
um,
function will get me more than one output in the same sense that like a square root would.
Yeah, if you make an inverse, then that's not really a function. At
Exactly.
best, it might be a relation, but it's not a function.
Yeah, which is actually another thing that I think the author is kind of like trying. He's on. I don't know. I didn't like the fact that he's used the term rule, right? He used the term rule for to talk about it instead of a relation. So that's a very careful choice of words.
Well, a rule is not necessarily reversible, which is kind of part of the point.
I guess you're right. If you state that it's a relation, you're automatically saying that it is reversible, right? I guess that is true. Anyway, so what we would do to prove that it's surjective without going to the number theory, and we cannot have an inverse because it is not injective, right? So I don't know. I would be kind of stuck on the surjectivity proof myself.
Uh, yeah, you can probably get away with just exploiting the fact that this is a cubic, right? This is a cubic equation. And importantly, there's no square term to complicate your proof. So you can just say, okay, unlike a square term, a cubic term can be both positive and negative, right? Because you have an odd number uh, of the same term. So you're not excluding the negative half of the numbers as an output. And then the linear term just shifts the graph around. It doesn't make anything undefined. So you can.
Actually, I have a question. Can we pick whatever Tevo found to be the pseudo inverse of this, and check if it has an undefined behavior, and if it doesn't, that's it? Can we use that? We're not going to be able to argue it as a function, but can you argue that all of those numbers from that algebraic expression can be contained in the exist in the output set?
I guess.
Again, we know it is not a function. Um, anyway, so function B exercise. Does anybody want to talk about something in here?
Can I just say that it's kind of fun that we're seeing a tangent here which has an undefined point, like for the second time, and we saw this last time as well, right?
I just noticed that after the arrow, there's no. What the fuck happened here?
Yeah, that's wrong. That should be an R, I think.
Well, but do I have that in the printed version? Let me check. I I do not. I do have the R. Okay, so this is a
Can
bug in the PDF version. Cool.
also B4 is kind of fun.
Okay, so it's a function from integers to integer, and we have to check either if it is injective or surjective. And
It is in fact bijective, but the definition is kind of fun.
okay, so how do we know? Okay, so it's injective because in all of those cases, necessarily all the n elements will go to different elements. So it is injective, right?
Yeah.
And it's also surjective because n plus 1 and n minus 1 are also in integers.
Yes,
All
and
of them are.
importantly, what this function does is it effectively flips each even number with its successor.
And it flips its odd number to its predecessor, right?
Yeah, like it takes pairs of numbers and just flips them around. So like, if you give it zero
Ah,
as
that
an
is
input,
true. It
you
flips
get
them
one.
around. That's cool.
If you give it one, you get zero, and then if you give it two, you get three. But if you give it three, you get two. You see?
Uh-huh. And what about B5? Find a bijective function f from the set integers of the set z of the integers to the set e of the even integers.
That's
Um,
just
that's
that's
just
just that's just f of n equals to n.
equals to n. Yeah, that does hold, right? Because this is always going to result in a different thing for every element of n, and every element of 2n is in the same integers z thing. So this is also surjective, which means that it's also bijective. Yeah, man, I like to overcomplicate shit because the first thing that went to my mind was modulo for whatever reason. But this is not. It is not injective, right? So
Yeah, modulo is the whole point of using modulo is that it's not injective.
yeah, pretty much. Okay, so C, functions on arbitrary sets and groups. So in parts 1 to 3, A, B are sets, and the Cartesian product denotes the set of all the ordered pairs as X ranges over Y and B over and Y over B. And then we have that what we need to do is
That's
to check if it's either injective or surjective, right? This is not injective, the one, right? C1.
nope. This is the drop function from fourth,
Only Marinho to come up with that one.
and the next one is swap.
Um, well, but here's the kicker, right? So this one is not injective, but this one is, right?
This is in fact bijective, the second one.
Okay, so this is also surjective, and yeah, I can see the reason why, because all the possible elements will be contained in the ordered pairs anyway.
Yeah, fun fact,
This
swap is
one,
its own inverse. So
yeah, sure. And the number one is It
Yeah,
is.
it's clearly like number one is clearly not injective because
Yeah, but what
no
about
matter what,
surjectivity?
it is surjective
It is
because if
surjective,
you
right?
get an yeah, if you get an arbitrary A, you just output that A.
Yeah.
The input is unconstrained, so the output will just be like this is just the identity function. If you ignore the second member of the
Yeah,
pair.
yeah. Anyway, anything interesting on the C exercises? Can we move on to D? Tevo, Marinho.
I think we can move on, I
Cool.
guess. Unless Tevo has something to say.
Not really, no.
D, so composite functions. In parts 1 to 3, find the composite function as indicated. So we have f and have g, and have f is a sine wave, and have g being an exponent. So then we have to find it. So this thing is essentially a Lego puzzle, right?
Yeah.
Because this is f after g. So this is what? Exponent of sine of x?
No, that's G after F.
G. Oh, that you're right. I got confused. This is g after f, and then after g is the sine of the exponent, right?
Yeah.
Um, you start with f and then you apply g. You start with g and then you apply f. And then a and b are sets, so again pairs. And this is doing the swap. G is grabbing the first. This is grabbing the second.
Yeah, it's literally just swap drop.
Yeah, this is grabbing the second. Let's okay. Uh, okay, then we have log 1 divided by x. Okay, the 4. In school, Jack and Sam exchanged notes in a code F, which consists of spelling every word backwards and interchanging every letter S with T. What an autistic way of like doing you're not supposed to be doing in school. Alternatively, they use a code G with interchange of the letters A with O, I with U, E with Y, and S with T. Describe the codes F composed by G and G composed by F. Are they the same? No, right?
Actually they are.
I don't think they are. And here's my argument. If you interchange, exchange, interchange every letter S with T first, um, that will not have any changes on this section of G, right? G only happens on the go S to T, but you don't have S's anymore because they already became T, right?
So what? If you switch every S with a T twice, that's just the same thing as doing it once.
Um, that's the same as doing it once.
We would have a problem if one of those codes exchanged T with something else. Then the order would matter, but it doesn't.
I think I see what my problem was. I didn't notice that S with T was being like, I don't know. I think I did in my head that this was not, they were not the same, these two things. And then, as you just stated, that would make it not the same. Like the order would matter. But I was wrong. These are the same. So never mind. Yeah, tabular form to do this, which is very easy, nothing special. G is a group, and A and B are elements of G. So we say that f is a function is defined by this and that, and you can compose them. And essentially, these are generators. This f and this g indicate the domain of range of each of the composite functions you found. Yeah, nothing too special on D. So let's go to E. Inverse of functions. So each of the following functions f is bijective. Describe its inverse. Describe its inverse. It's just a matter of doing manipulations, isn't it? Oops. So
Describe its inverse.
this will become, I don't know, x. This will be log. Then here you have to do something about. Of course, that you have to check if these functions are within the range, right, of the
Um,
thing.
Parentheses are closed intervals, right?
I have no memory of that. I don't remember.
Parentheses, from what I remember, they do not include the endpoint.
Yeah, f of x is its own inverse in one in that case. It would be undefined because if 0 was included, but it isn't.
You mean E1? This f is its own inverse?
Yeah,
Wait, f is its own inverse.
oh yes, because if you take the reciprocal of a number that's greater than 0 twice, that's just the original number, right?
No, I guess. I guess that is the case. I guess that is true. Yeah, I guess that is true. Um, anyway, so anything that you guys want to talk about in E exercise?
Not really, but I just like to mention that I am silly, and the inverse I found for the other function is wrong because I replaced y in a place where I should have replaced x.
Yeah,
Ah.
no, that's also very easy. That's a very easy mistake to make as well.
So there is, I am almost convinced there is no way to algebraically manipulate that in order to isolate x, but I cannot prove that yet.
Yeah, and which means that what I said before, if you cannot get an expression, is also fucked up because I was kind of relying on what you said that you found something. To prove this is surjective or not, then you're probably gonna have to do what Marinho said with the number theory thing, which kind of sucks. Okay. Functions on finite sets. So we have a committee which must choose the president, the presiding officer of the committee. For each member X, let F designate that member's choice for officer. If no two members vote alike, what is the range of F? Isn't it all of them?
Yeah, the range and the domain are equal in this case.
Yeah. And the reason why is because to prove it formally, you can do some sort of induction. You can say that the F of a particular officer x1 is going to be another particular officer xn, in which n is within the range blah blah blah, but it's different than 1. And then in the f of x2 is the same, but removing the vote of x1, and then blah 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 blah. And at the end, the last guy is going to be unlucky because he will have to vote for the remaining one.
Yeah.
Which is kind of like, that sucks ass. Uh, okay, so with that out of the way, number
I mean, that is
two.
a silly way of picking a president because you're never going
That's
to
terrible.
pick anybody anyway.
Yeah, that's terrible. That's
Yeah,
terrible.
the only way to get a result here is if the committee has only one member.
Yeah, it's very
But
terrible.
then you have a bigger problem because you have a committee that only has one member. How
Actually,
did that happen?
I take that back. There is a way, which is not to say that it's a good way, but you can say that the president's going to be the last one remaining. So the ones that vote first, they have eliminating votes. They are cutting you off of the chance of becoming president. And the last one remaining in the pool is going to be the final president. So like, let's say that I don't want Marinho. I think Marinho would be a terrible president. If I vote first, I'm going to cut Marinho off the list first. You see?
I see.
That's anti-democracy. You vote for
That's yeah,
the
yeah.
one
That's
one.
100% not what they're aiming for.
You have vetoes instead of votes.
Exactly. Yeah. But there is one way to make sense out of this madness here. Let A be a finite set. Explain why any injective function f is necessarily surjective. f in this case going from A to A, like the domain is equal to its range. And the reason is because by the definition of injectivity, well, by the definition of f, all the members of A are being used. And by the definition of injective, they are mapping to all the elements of A as well, because there's nobody remaining on A, on the image. So then it must be surjective, right? Something like that?
Yeah, it's basically the same proof as 1, essentially.
If A is a finite set, explain why any surjective function is necessarily injective as well. So we know it is surjective, which means that all elements of A are being used on the image, but because they are all being used, and this is a function, that must mean that all A elements in the domain are also being used, so it's injective. It's just 3 different ways of explaining the same thing. Other statements imply
Yeah.
truth and 3 true when A is not finite. If not, give a counterexample. So let's pick integers, for example. Can we
The
make a
doubling
function?
function.
The doubling function.
Yeah.
I don't. Wait, the doubling function is a counterexample?
It's a counterexample. Yeah, because it is injective,
Yes.
right?
Yes.
But it's not surjective because you're clearly not returning, let's use a programming term, you're not returning any odd numbers, right?
Oh yeah, that is definitely true. If A has n elements, how many functions are there from A to A? How many bijective functions are there from A to A? I don't know how many. This is a prologue question. What are you talking about?
No, it's n
Huh?
factorial. Or rather, let me put that in a different way. If it's functions in general, it's n to the n, and if it's bijective functions, it's n factorial.
Yeah, I
Is
thought
it
it would
not?
be n to the n. Go Tiv. Yep.
Is it not 2 to the n? Because you have n elements and you're combining 2 of them.
No, this is a function from A to A, right?
Yes. And they
That
have n
means,
elements.
yeah, it has n elements, right?
Yes.
Which
That's a very good
oh
question.
yeah, actually no, it's not really n. You're right because
It's a function that can make any 2 pairs, right? So yeah, I think it is 2 to the power of n.
no, it's not any two pairs. It's like how many functions do you have from A to itself, basically? That's what
Exactly,
he's
but
asking.
no, yeah, but that ends up if you take a look on if you group all the possible pairs of all the possible combinations of functions available, that will necessarily generate all the possible pairs, isn't it?
Um, all the possible pairs.
Yeah, grab all the outcomes of all the possible functions from A to A.
You mean all the possible triplets?
Not
Triplets.
triplets. This is a
What?
function from A to A.
This
I
is a
mean,
function from
considering
A to
that.
A. Like, let me give you an example
Yes,
so
that is a
everybody can.
function. That is a function from 2a's to a third a. That's why triplets.
No. This is a
No,
function from A
no,
to A.
no. It's a function from A to A, which means that a
Which means
function
it
f1.
combines 2a's into a third a.
No. Wait, is this what you were. Mane, what are you understanding?
It's a function that takes an A and returns an A.
Exactly.
Oh, okay,
What
sorry.
Tevu is understanding is
That
grabbing
is
a pair and returning an A.
Yes, no, sorry. I am thinking of
Okay, so my
an
argument,
operator.
my observation is the following, Maria. Imagine a function f1 that in particular is going to generate, I don't know, a1, b1. Oh, these are the possible inputs and outputs combinations that function f1 is going to use from A to A, okay?
Okay.
If you do that for f2 and you sum that up with F3 and F4, blah, 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 isn't this eventually going to generate all the possible inputs with all the possible outputs of A? Or am I tripping? Because if that's the case, then 2 to the power of n makes sense.
2 to the power of n.
Yeah.
2 to the power of n. Well, let's see. Okay, so a function must be defined for every input, right?
And just a reminder, we have the answer to this exercise, so we don't have to be stuck on this one.
No, I'm pretty sure it's n to the n because we saw this exact same thing back when we were reading about category theory.
It makes n to the n makes sense. Yes.
I don't know. Wait, can anybody explain to me why it would be n to the n?
Because this is not really about it's not really about enumerating the input-output pairs. It's about, okay, how many different ways there are to do those enumerations, right? Yeah, because in general, let's use freaking booleans as an example, okay? You have two elements in the set, right? So how many different functions can you make out of that? Clearly, you have the identity function, that's the trivial one, right? Just maps each element to itself. Then you have the two constant functions that just ignore the input and give you a fixed output, right? And then you have the only interesting function, which is negation, that flips the input. That's 4, right? Which is 2 to the 2.
Well, but that also fits into the 2 to the power of n example. We need to generalize this to n of n.
But then if you add another state, for each one of the possible states, you have another possible state, so that becomes 3 to the 3 again.
Okay,
yeah,
let's also read this one before. I think I understood what you guys are explaining, but let's read the answer from here from the author. Let A have these elements. If f is any function from A to A, there are n possible values of f of A of x, namely a1 to a of n. Similarly, there are n possible values for a true. I see. Yeah, so this is going to end up with n to the power of n, as you guys said. Thus, there are n square pairs consisting of a value of f to the f with a1 together with a value of a f to the a true. Similarly, there are n cubed triples consisting of a value of a1, a2, a3. We may continue in this fashion and conclude as follows. Since function f is specified by giving a value of f to the a1 all the way to f to the an, there are n to the power of n functions from a to a. Now, by reasoning in a similar fashion, how many bijective functions are there?
n factorial.
Okay, why?
Because
for every step, you have one less valid element to be able to map to, so you end up with a factorial.
Yeah, that's the short version.
I see. Yeah, that makes sense. But the trick here is to think that
if you're here's a way to get that more intuitively, Lemos. If you consider just finite sets, then clearly what you have to do to construct a bijection is you have the list of elements, which is the input, right? Let's use the notation they introduced where you have a matrix with 2 rows, right?
well,
The
the
top row is
intuition is
just
that every time you consume an input element, you are also consuming an output element, and then that's why the exponentiation becomes factorial.
well, yes. The other way to get the same intuition is to say, okay, if you look at just the finite case, then you can write a function as a matrix, as we saw earlier, right? And then for it to be bijective, you basically say, okay, each element that appears at the top must appear at the bottom exactly once, but the order doesn't matter. So you get all
Yeah.
of the permutations
Yeah,
of
yeah,
that.
that's a perfect way to explain it, I think. That's the best way using the matrix. Yeah. Good job, Marinho. Some general properties of functions. So yeah, this is proving. Well, this is related to the proof that we were talking before about. Oh, if the composite is injective, then f is injective. And prove that if g after f is surjective, then g must be surjective. Mm, okay. Okay, so to prove the first one, that f is injective, we need to use the fact that the... Well, this is actually pretty easy, isn't it? Because if the composition... Oh no, but f is the beginning of the composition. Never mind. G comes after. G comes after. Mm-hmm. So how would you guys go about this one?
Uh, well, for g of f to have any possible hope of being injective, then f must be injective, because otherwise, if f is not injective, then there must be some input, some pair of inputs which give the same result after you go to f, right?
Yes.
And then no matter what g is, those two inputs will map to the same output,
And then the
because
G after F will not be injective, and that contradicts the premise.
yeah.
Okay, what about the second one? So if G is not surjective, that means that there are some remaining elements on the output thing, right? Which
Yeah, no matter
means
what f
that some
is,
inputs of F
then
will be undefined. That's what I'm guessing.
no.
Or G won't be undefined.
No. But G relies on the what F is gonna do anyway. That's why I said F. Go on, Marie.
Basically, g uh, for g after f to be surjective, assuming that g isn't, um, what's gonna happen is it doesn't matter what f is, like, because whatever f gives to g, um, it will do its thing and give an output, right? But g, whatever g gives out is going to be the result of the entire composition, and we
Yeah,
know
that's
that
always, yeah,
g,
that's actually easier than one, isn't it? Because if this is surjective, this and G is the last operation being applied, and the end of the composition is surjective. If G is not surjective, the composition would not be able to be one.
yeah.
So that's actually easier than one. Sorry, Tevo, do you want to say something?
Not really.
Okay.
When I said G is undefined, I mean there's some value uh, on the output set that is not on the value
And
on
that's outside of the range.
that G cannot map to,
Yeah,
which is not really G being undefined.
yeah. When I said undefined is because I was trying to claim that there will be an input F that doesn't necessarily will be able to find an image because it's outside of the range of G. But that doesn't need to be the case because G can just map it to something else. So I was also wrong in what I said. Parts 1 and 2 together tells us that if G after F is bijective, then F is injective and G is surjective. Is the converse of this statement true? What is going on?
Yeah, that's messed up.
What is in the
That should
real book?
be that should be F, I think.
Let me check what the book says. The printed version. So this is in the G exercise. Okay, so hey, that's F, definitely. If F is injective and G is surjective, is the composition bijective? If yes, prove it. If no, give a counterexample.
Well, there's a very easy counterexample. If f is a function that takes a boolean and returns some ternary value, so like from a set of two elements to a set of three elements, and then g goes from that set of three elements to another set of two elements, then um,
Then?
g after f.
Yeah, that.
Actually,
Okay, go on.
if f is injective and g is surjective, no, that should be backwards, no?
What? No, F. No,
No, oh no, okay. If f is injective, so
that means
and
that
g,
all of the elements are going to different elements in the image. And G being surjective means that we're gonna use all the range. If those two things are true, is the composition bijective then?
is the composition bijective.
Yeah, because we proved the other way around.
Well, if g is not injective, then I don't see how g after f can be bijective.
You said G injectivity. That we don't care about that.
No, if g is not injective, I mean,
Yeah, but we don't care about the injectivity of G. We care about
no,
its
no,
surjectivity.
no. We know that it is surjective by because that's the primitive. That's the premise we're starting with, right?
Yeah.
Um, okay, let's suppose then. Hmm,
Man, I think
okay.
the answer is yes, but I don't know how to prove it. Like my
Hmm,
intuition is telling me that it is yes. Because here's what I'm thinking. If F is injective and I'm doing that first, that means that I'm going to the domain of G with all the elements mapped, right?
but what if g is not injective, Lemos?
Wait, no, wait, but I'm talking about F. I'm talking about
No,
F.
no, no, no. We're assuming f is injective. G may or may not be
Yeah,
injective. It
but I'm
doesn't. It,
yeah, but I'm talking about F. So hold on.
okay,
So if F is injective, what does that mean? That means that we are mapping all the elements of F in the domain of F to different values in the domain of G, right? And,
right.
and they are all different. So no, yeah. So that's what I'm trying to say. But if G is surjective, then it means that going from the domain to its image, we're gonna use all of the image, right? So from the perspective of the domain of F and the image of G, is that not bijectivity?
What happens if the output set? What happens if C, which is the domain of G, is a set with one element?
One element. Then F
Yeah.
is not injective.
No. Then G is not injective.
No, F is not injective.
No.
You said
G. I'm talking
C.
about.
No, you said C. Oh, you said C domain of G, but you meant C image
Uh,
of G.
yeah. No. The codomain, not the domain.
Ah, okay. So if C only has one element, then that depends on the injectivity of G, which we don't know,
It
right?
cannot be injective because, well, it can only be injective if B has one element. But what if it's
No, but if
like there
B
is a
if B has one element, then A must also has one element because F is
no no no
injective.
no no. But what happens if okay if A has two elements and B also has two elements, but C only has one?
Then G after F is not bijective.
There you go.
Dev, did you follow that?
It makes sense, yes.
Okay. Let F. Yeah, I think Marinho is totally right because we need to know about the injectivity of G to talk about this. By letting it be loose, that example of going from a set of n elements to a set of n elements, but a set of elements that is smaller than n that allows G to not be injective, and if that's the case, then the whole thing falls apart. Let f and G, blah blah blah, suppose that, prove that if is bijective, then G is equal to the inverse. Do you want to do this one? We already are above on 1 hour, so I don't know what we're gonna do. So do you guys want to do this one or not? Can we move on to automata?
Yeah, this is important, but it's not that interesting, honestly. I think we can move on.
Okay. Okay, and then it's explaining state machines, finite state machines with finite automata. Again, we know computer stuff, so this is very natural to us. And then there's the table, which is also a classic thing. Man, it's been what? It's been 8 years since I've seen this the first time. Then there's that, and you can use a state diagram, which is also a classic thing. Yeah. Okay, so let's try to be very fast here because we already are above an hour. So any exercise here from H section that you guys want to talk about?
Uh, Not really. Most of those are just about counting.
Yeah. And there is a transition function. Explain why M1 has only two distinct transition functions. Two functions f and g are equal only if extinctionality again. Yeah, I don't think there is anything like that I remember would be like, oh my god, this is something something. The input alphabet consists of four. For each incoming sequence, the machine determines whether the sequence contains exactly three A's. Um, yeah. Let's see the answer to this one. Next stage function is described by the following table. Boom.
Yeah, basically you should be able to count to 4 from 0.
Yeah, so if you are in state 0, which means essentially how many A's you already have, that's what the state we are holding. If you encounter B, C, and D, then you keep on 0 if you found an A, same thing, same thing, same thing. Um, but why do we have to have 4 of these instead of only 3?
Because you need to know if A appears exactly 3 times, right?
Yeah, but I'm counting the
So
4th time with this A here.
No.
the
It's because
fourth
you say,
time,
I haven't seen any A's yet, so that's 0. I have seen 1 and 2 and 3. But then the fourth time is, okay, I've seen 4 or more A's, so it doesn't match, you see?
Dave?
I was going to say what Marina just said.
Okay, so the 4th A.
Yeah, the fourth state is just to say, okay, we went over 3, we don't match anymore.
But it is written here, if the machine ends in a 3, the sequence has with exactly 3 A's. So I don't know why this is here at all.
Because what happens if you have 4 A's in the input? Or 5, or 6, or 7, or 8?
Ah, okay, so this is to take into account if the input has, like... It's the difference between at least 3 and having exactly 3.
Yeah.
I see. Okay. Cool. So let's talk about I. So then it talks about semi-groups, which is kind of funny that we didn't go over them. We jumped straight up to groups. We have semi-group mean a set A with an associative operation. There does not need to be a identity element, nor do elements necessarily have inverses. Every group is a semi-group. Uh, I just noticed that group is a monoid.
Well, every group is a monoid because you have a neutral element, right? And it's associative.
Yeah, but I just noticed that in Haskell we do have this name, but we don't use this name. Interesting. Uh, the converse is clearly false, right? Because not every semigroup is a group. With every semigroup A, we associate an automaton M called the automaton of a semigroup. The alphabet of M is A, and the set of states also is A. The next state function is that. Assuming the operation can be denoted with addition. We can talk about this one. Man, this looks so fucking close to a state mono, doesn't it? Describe MZ4.
I mean,
Go
I
ahead.
mean, this is basically a left fold, right? Except the direction of the fold is irrelevant because this is a semigroup.
Yeah. Yeah, that's why in monoids we don't have a fold L or fold R. We only have fold. Describe MZ4. That is, give the table of density functions as well as the state diagram. This is the modulo thing, right? With integers. And what the fuck is S? Right?
Yeah, this is something that actually only appears in the next chapter. I'm not sure why it's here.
We already read the next chapter. Groups of permutations.
Yeah, it's actually pretty interesting.
Okay. Okay, anything interesting on the ICE exercises, folks? I kind of have to go. Kind of.
Not really. Automatons are like pretty freaking common for us, so we've seen it 100 times already.
Yeah, it's a kind of thing that we use it all the time, but nobody talks about it. Uh, so what the heck is the T thing? So transition functions. Since
It's
the
a transition
compositions of
function, yeah.
functions is associative, it follows that the set of all transition functions with the operation compose is a semigroup. It is denoted by that. It's called the semigroup of the machine M. Um, so Tevo, do you have anything about this set of exercise that you want to highlight?
Not really, no.
Marin already said no. Um, yeah, this is mostly about drawing things, in my opinion, like drawing these things and drawing the tables. You're probably gonna solve all the exercises by doing that. Okay, so anything else, folks, before I can finish the recording?
This was a fun chapter.
Yeah, functions are fun. Functions are actually pretty fun. And but well, we are starting to like. I think this is gonna get terrible at some point because but this is not in particularly about this book. This is in particular for all the math books. The definitions that are gonna pile up, and we're gonna go to like chapter, well, I don't know which one we are. 7. We're about to go to 7. Yeah, when we are in chapter, I don't know, 15, there will be so many definitions composing on top of one another that we're gonna have like ethereal discussions about the existence or whatever. That always is the case. That's what I learned.
All right.
Oh, I know you already moved on, but I was going to say you cannot spell functions without fun.
Yeah, Lemos didn't notice. I was waiting for him to notice, but he didn't.
Well, I did notice, but I just didn't highlight it. I'm gonna finish the
Okay.
recording right now.